We spent a lot of time talking about charge distribution in molecules and spending a lot of time talking about how molecules interact with one another. Now it's time for us to fill in some of the missing gaps and talk about intermolecular forces. Our learning goals for this will be learning about the characteristics of different types of electrostatic intermolecular forces and the relationship between intermolecular forces and physical properties that occur on a macroscopic scale. So let's review what we know about electrostatic forces. Remember that they're based on Coulomb's law, which is written like this, that the force is proportional to a constant k times the product of the two charges divided by the separation squared. So to remind you that Q1 and Q2 are the charges, R is the separation distance, and K is a physical constant that basically helps us set the units. So the larger the charges are, the larger the force will be. The larger the separation distance, the smaller the force will be. So we look for small separation distances and large charges. So Q1 and Q2, if they're larger, will have a stronger force. If they're closer, will have a stronger force. So now let's look at dipole-dipole forces. So this is going to happen when we have a molecular dipole. Remember, the dipole is a charge separation that's attached to the same body. So we have a positive end and a negative end. There are different ways that we could arrange dipoles relative to one another, and the forces that are due between these dipoles are going to be due to the partial charges. So for example, if we have the positive end of one next to the negative end of another, these will be attractive Coulombic interactions. We could also have a parallel dipole interaction where we've got the positive end of one next to the negative end of the other, and the opposite true at the other end of those dipoles. So these are different ways that these can combine to enhance the strength of the electrostatic forces between these dipoles. I should note that these dipole-dipole forces are weaker than charge-charge interactions. This is true in part because the delta is going to be less than 1, but it's also just true in part because these are they're not as direct as the Coulombic forces that we see in a charge-charge interaction. They're also going to be stronger for larger delta and smaller separations, just as they are in the case of the Coulombic interaction. There's another kind of intermolecular force that arises from electrostatic forces called dispersion forces. Now, this is a more subtle form of force, and it's something that really has only been discovered, I guess, since the advent of quantum mechanics and our quantum understanding of molecules. And it helps us to explain why molecules that do not have dipoles still stick together, still have an attractive intermolecular force between them. Basically, it comes about because these electron clouds in each atom are polarizable. This means they can deform and shift as they're around the protons, around the nuclei of the atoms. When these electron clouds shift, they form a positive end and a negative end in a transient way. So this creates, if you will, an induced dipole around that atom, and it gives a picture that looks something like this, where you see in the induced dipole picture, the induced positive end of one is attracted to the induced negative end of the other. And this is simply due to the fact that these are mobile clouds, and as they shift around, the electrons on one might see the nuclear charge on the other more clearly, and therefore be attracted to it. These particular induced dipole-dipole forces are called London dispersion forces. London was the name of the scientist that first proposed this. It's not named after the city. I'll call them dispersion forces for short because it's a completely general phenomenon. It typically tells us that larger atoms, which are more polarizable because they have a larger electron cloud, are going to have stronger dispersion forces. So that means that as we go down in the periodic table to lower elements in the periodic table have larger orbitals. Those larger orbitals mean their atoms are larger and they're going to be more deformable and therefore have stronger dispersion forces. You should note that all molecules have this effect. So even small ones have some amount of dispersion forces contributing to their intermolecular forces. It also explains why when you freeze down even the noble gases, they will stick together to form liquids and even solids. This leads us to considering the physical states of matter and the effect that these intermolecular forces have on it. Obviously, the strength of the intermolecular forces determine how well molecules stick together. whereas temperature determines how fast they move. So what it means is that strong forces between molecules means a higher temperature is needed to pull them apart. And weaker forces means that they can still be a gas at low temperature. So as we look at the different phases, solid phase is one where the molecules are not moving fast enough to break apart from one another. In a liquid phase, they're moving a little faster so they can, and in a gas phase, they're moving fast enough to overcome those intermolecular forces and be essentially separated from one another. So this means that we can observe the strength of these intermolecular forces indirectly by observing, for example, the states of matter at room temperature. If it's a solid at room temperature, then the intermolecular forces are generally pretty strong. If it's a gas at room temperature, that means the intermolecular forces are fairly weak. We can also observe this by looking at the temperatures of phase changes. So the higher the temperature of a phase change, the stronger the forces are between the molecules in that substance. So when we look at these various kinds of intermolecular forces, their strength varies from the weakest being the dispersion forces up to the strongest being a charge-charge interaction. Charge-charge interaction really is the bonding in an ionic compound. Now, even though the dispersion forces are the weakest of these, they're present in all molecules and they exist throughout a molecular system because they all have electron clouds that can be deformable. So we'll find that the cumulative effect of dispersion forces sometimes is even greater than the effect of a dipole-dipole force, even though the dispersion force itself is weaker. So let's test the concept. I want to consider two compounds, basically dihalogenated ethylenes, so difluoroethylene and dichloroethylene. And in both cases, I'm going to arrange these things in a particular way. I want you to notice that these are arranged so that the bond dipoles for the carbon-fluorine bonds in the first molecule and the carbon-chlorine bonds in the second are pointed in opposite directions. This means that they have a zero dipole moment. Those bond dipoles cancel each other when we add those vectors together. So there's no dipole moment for these molecules, even though they do have charge separation. They will have some Coulombic interactions because of that, but it affects the strength of their intermolecular forces. Well, we find at room temperature, the first of these, CH2F2, is a gas, whereas the chlorine variety is a liquid. Now, that would imply for us, based on what we've just said, that the intermolecular forces of the difluoroethylene compound are weaker than those of the dichloroethylene. The intermolecular forces are. Yet both of them have charge separation. We know that the carbon-fluorine bond is in fact a more polar bond. Both of them have a zero dipole moment. So that leads us to ask, why are the forces in the dichloroethylene stronger? Why don't you think about that? If you need to pause the video, you can. I'll give you the answer in just a moment. So let's think about the other things that are different between these. They're very similar in many ways with the charge separation and the lack of a dipole moment. But one thing that's very different between them is that chlorine is a much larger atom. That means its electron cloud is more deformable. So in fact, it has stronger dispersion forces than the difluoroethylene compound would. And it's the greater strength of these dispersion forces that causes the dichloroethylene compound to be a liquid at room temperature. So you can see, even in a case where you have no dipole moment, but you have charge separation, that the dispersion forces can be conclusive in separating the behavior of two compounds.